So now that we have a couple of equilibrium problems under our belt, what if we change the initial concentration of HPR in our previous example? How would that actually affect the amount of HA that dissociates, right? So let's go back to our previous example and look at these questions. So here we had 0.10 molar HPR, and now we're going to decrease that concentration to 0.010 molar HPR. We want to know, okay, if I decrease the concentration of the initial amount of this weak acid, what is going to happen to the percent that is going to dissociate? Of course, if I change the initial amount, that means I'm going to have a different X value, different H3O plus concentration, etc., etc. Then, of course, a different initial amount, completely different Rice table, but the setup of the Ka expression will be similar. So we have our initial amount from the previous example of 0.10 molar. We're going to effectively decrease it to 0.010 molar. And what happens when we do that? What is actually observed? Well, guess what, folks? What is observed is that the percent dissociated of our weak acid actually changes. And it ends up increasing to favor more molecules of ions based on the fraction of ions present using a brand new expression. That expression is called percent HA dissociated. And it's equal to the concentration of HA dissociated divided by the concentration of HA initially times 100. And HA is going to represent our weak acid, right, folks? With this expression, it helps us understand how a decrease in the initial concentration will cause an increase in the percent dissociated. So when our HPR initially is 0.10, you get a percent dissociation of 1.1%. But when we decrease it to 0.010, we actually get a percent dissociation to 3.6%. So we have an increase here, folks. And because of this, a trend is revealed. The fraction of ions present using this particular expression is going to show us that we have an increase in our percent dissociated when we have a decrease in the initial concentration. Okay, folks? Now, what happens when we're outside of using this particular expression? Well, we got to go ahead and write out our weak acid, mix it with water, and get our H3O plus and our conjugate base. Outside of using this expression, if we were to decrease HPR, what's going to end up happening? Which direction are we going to shift our equilibrium? So let's think about it. If we were to increase this overall reactant, we know we're going to produce more products. So if we were to decrease this overall reactant, we know that we have to produce more of the reactant in order to get back to equilibrium, correct? So that is completely opposite of what we see when we use this expression. That's why it's going to be important to understand using the expression was when you need to, and then understanding how to apply it to equilibrium principles like Le Chatelier's when you just need to understand a shift. Another way to think of it is if I'm lowering my HA, it's going to shift to the position where it's going to favor more molecules because we want to be able to have that increase there to show us from this fraction. And so I can also say from my overall expression, remember this is expression based, so I'll put it in a different color. We are shifting to the right. So the expression we're shifting to the right. With regular old equilibrium, Le Chatelier's principle, we are shifting to the left. And it's always going to be important to distinguish the two. And the way you distinguish it is based on whether or not you're using this expression. If you're not using this expression, you go off Le Chatelier's like normal. If you are using this expression, then we have to go off of what happens when we use this expression. And what happens is when you decrease the initial amount, you effectively increase the percent dissociated. All right, so we're back to the Avengers compounds for some examples. Let's go ahead and read the question, bring up any necessary expressions, relationships, assumptions, etc. So in 2011, researchers showed that hypochlorous acid, HClO, generated by white blood cells kills bacteria. So we automatically know this is a weak acid because it's an oxo acid and it's equal amounts of oxygen and the ionizable proton. It says calculate the percent dissociation. So that means we've got to go ahead and bring out our overall expression. As soon as I see it, I'm like, let me go ahead and bring out the expression. The concentration dissociated divided by the initial concentration times 100%. Okay, boom. They want us to calculate the percent dissociation of a 0.4 molar concentration of HClO and a 0.035 molar concentration of HClO. We have a Ka value of 2.9 times 10 to the negative 8. And of course, since we're talking about the same weak acid, this Ka value is going to be used for letter A and B. So just like every other weak acid at equilibrium type of problem, you know you have to have a Rice table. You know you're going to be using any expressions possible to help you make those relationships. For us, it looks like our plan is simply going to be to set up our rice tables once we have our balanced reactions to simply figure out the the concentration of HA dissociated, which is going to equal our X value in our rice table, and then divide that by our initial concentration that's given here. And as you can see, letter A and letter B is going to be a decrease in the concentration here. So we definitely should see a trend that we should see an increase in percent dissociated just because we have a decrease in the initial concentration. So let's go ahead and get into letter A. All right, first things first, for letter A, our initial amount is going to be 0.40 molar. We have HClO here. So I'm going to set up my rice table. My reaction first is going to be HClO, which is my weak acid, mixed with water to produce H3O plus because it donated a proton. And then we're left over with ClO minus, which is its conjugate base. Okay. Next, I'm going to fill in my rice table. 0.40 molar to start initially, 0 for my products, minus X plus X over here. So this is 0.40 minus X, and then we have X and X for our equilibrium amounts. Now, we have a Ka value that's already given. It's 2.9 times 10 to the negative 8. So with this, I know that I definitely can make an assumption here. So I can assume. And because I can assume, I can get rid of what? I can get rid of my minus X here. So that way, when I write out my Ka value, it's going to equal my products divided by my reactants. My product equilibrium amounts are X and X, divided by now 0.40 molar. This entire thing is equal to 2.9 times 10 to the negative 8. Now, what am I going to do? Cross multiply here, these two numbers, and then take the square root in order to solve for X. Once I've solved for X, I have effectively solved for the H3O plus concentration and my conjugate base concentration, which equals the concentration of my weak acid that was dissociated. And I can use that here. I can take my initial amount that was given here and solve for the percent dissociation. Okay, I cross multiply these two numbers. I get 1.16 times 10 to the negative 8. I'm then going to take the square root of both sides, and I get X is equal to 1.1 times 10 to the negative 4. So this is my X value here. Now, once I have my X value, that's going to equal to the concentration of my weak acid that's dissociated. So now I have this value. This value is already given. I can go ahead and go further and plug in all my numbers to my percent dissociation expression. So I have my 1.1 times 10 to the negative 4 divided by my initial amount given, 0.40 times 100%. And what I get is 0.028%. And that's how we get the percent dissociation for letter A. Now let's move on to letter B. Okay, so for letter B, we're still going to set up our rice table here. We have our HClO mixed with water to produce H3O plus and the conjugate base. Now, instead of starting with 0.40 molar initially, we're starting with 0.035 molar. And so that'll be my initial amount here. We're still going to have minus X for our rice table and plus X here and plus X here for our products. Now, for our equilibrium amounts, we're going to take 0.035 minus X. And because our Ka is the same and we can make an assumption, we automatically get rid of that minus X here. And so we have our Ka expression written down, our products divided by our reactants. We're going to get X squared divided by now 0.035 molar. So after this, it's basically essentially the same setup that we had for letter A with our different numbers, of course. So I'm going to take my 2.9 times 10 to the negative 8 and cross multiply with 0.035. I get in my calculator 1.015 times 10 to the negative 9. I'm going to take the square root of both sides so I can isolate and get X by itself. When I take the square root of this 1.015 times 10 to the negative 9, I get X is equal to 3.2 times 10 to the negative 5. Now I have my concentration of my weak acid that has been dissociated. I'm going to take that number, 3.2 times 10 to the negative 5, and divide it by my initial amount, my new initial amount that's given. And that's going to give me my percent dissociated, or that fraction of those ions, once I multiply it by 100%. I get 0.091% as my final answer for this second initial amount. And that definitely makes sense. For letter A, if we got 0.028%, if we therefore decrease the initial concentration, we definitely should see an increase in the percent dissociation, which is exactly what we see.